Hello everyone, my name is Maggie Tansky and today I will be walking you through my report for Lab 4 oscillations. In this lab, we will use Tracker to analyze the motion of a mass oscillating on a spring attached to a fixed point. We determine the system to consist of the mass, the spring, and the earth. In this case, we will make the assumption that the mass of the spring is negligible and the fixed anchor point does not do work on the system. We will use GlowScript to construct a computational model of a system identical to the one from Tracker and compare the two in our discussion. In Tracker, I set the origin to be the fixed anchor point with the negative y direction pointing straight down. After plotting each point in the motion of the mass spring system, I copied the x and y coordinate data into a CSV file for later use. In order to find the period, or t, of the mass's oscillation, we must subtract the time from the initial point from the time from the final point and divide the result by 3. This will give us the average of the period for these three oscillations, which is 1.519 seconds. We will then use t to solve for the stiffness of the spring. Since t is equal to 2 pi times the square root of mass over spring stiffness, we can rewrite this equation as k is equal to 4 times pi squared times mass over period squared. We then plug in the mass, which is 0.402 kilograms, and the period, which is 1.519 seconds, and we find the spring stiffness K to be 6.869 newtons per meters. Next, we will solve for L0, the relaxed length of the spring, using the spring stiffness. As you can see, in this case, the magnitude of the force of gravity is equal to the magnitude of the force of the spring. Therefore, mass times gravity is equal to the spring stiffness times the stretch, which is the stretch length minus the relaxed length. We can rewrite this as L0 is equal to the stretched length minus the mass times gravity over the spring stiffness. We find that the relaxed length of the spring is 0.1265 meters. Our initial conditions include the mass, which is 0.402 kilograms, the initial position of the mass, which is a vector of negative 0.114, negative 0.6310 meters, the initial velocity of the mass, which is 0 meters per second, and the initial time, which is 0. We also set delta t equal to 1 over 210 seconds. Our other initialization includes the gravitational constant, 9.8 newtons per kilograms, the spring stiffness, 6.869 newtons per meters, and the relaxed length of the spring, which is 0.1265 meters. We set L to be equal to the position of the mass minus the position of the spring, L hat, to be over the magnitude of L, and S to be equal to the magnitude of L minus L0. Because we set the system to include the mass, the spring, and the earth, there is no external work done on the system. Therefore, kinetic energy is equal to 1/2 times the mass of the ball times the square of the ball's velocity. Gravitational potential energy is equal to the mass of the ball times g times the y position of the ball, and the spring's potential energy is 1/2 times the spring stiffness times the square of the stretch. At each step, while t is less than 9.307 seconds, the current value for kinetic, gravitational energy, and spring potential energies are defined as initial. Then the force of gravity is defined as a vector 0, ball dot m times negative g 0 newtons, and the force of the spring is defined as negative k times the stretch times L hat. Net force is defined as the sum of the two. Next, we update the velocity using Newton's second law, and we then update position, stretch length, L hat, and stretch. Next, we update the kinetic, gravitational potential, and spring potential energies. We'll use these updated values to find the change of each energy by subtracting the initial value from the new one. Using the energy principle, we determine that the total energy of the system E is equal to the sum of the kinetic, gravitational potential, and spring potential energies, and the change in total energy is equal to the sum of the change of the other energies. When we run the program, we must upload the CSV file mentioned previously. I set the rate to 500 so we aren't here forever. We see that the blue dot, representing the computational model, and the red dot, representing the motion analysis, have similar but not identical paths. Because we defined our system to include the mass, the spring, and the earth, there is no work done on the system by the surroundings. Therefore, the total change in energy must equal to 0. In the change in energy versus time graph, the yellow line represents the change in total energy. Here, I have plotted the x and y position versus the time data. As you can see, the x position data has a higher amplitude but a shorter wavelength than the y position data. From t0 to t2, the graphs appear to be somewhat mirrored as their troughs line up, but this quickly ceases to be the case as the x position data is more bunched up than the y position data. I use the y position data when determining the period for my lab.